is now. All right, so today we are getting into what I would consider one of the most important parts about chemistry, and that is chemical equations. You will hear me use the term chemical equations and chemical reactions. You'll hear me use those terms interchangeably. Um, and so if I say that, if I use those two, yeah, they are interchangeable, and I wouldn't stress about that. Now, with that in mind, let's go ahead and kick things off. So again, we're going a little bit, not necessarily backwards, but we finished chapter 6. Now we're going to 5. We have 7 and 8 after that, and then we have our final exam. So 5 we're going to knock out this week, and then 7 and 8 we'll tackle next week. And whenever it comes time for your final exam, I'll give you a little bit more insight into that and the content that's going to be on it. It's going to be a comprehensive exam, but there will be a little bit more emphasis on the more recent stuff that hasn't been tested over. So your exam this upcoming Monday will cover 5 and maybe a part of 7. I don't think much of 7, but at any rate, here we go. So, over the course of this semester, we've talked about a couple of different things. We talked about physical changes. So we talked about what you can actually see, what you can visualize. For example, a liquid converting to a gas, and then a gas converting to a liquid converting to a solid. These are all things that you can see. These are tangible things. Now, what that translates to, or what's important to know about, is what is happening on the microscopic level. Here, for instance, we have a water molecule, another water molecule, and it's kind of tough to see, but let's focus in on this water molecule right here. And if you look closely, you'll see a couple of blue lines or blue bonds, blue connectors between and I'm going to shade in, or I'm going to put an X over an oxygen atom and another X over a hydrogen atom. So that would be an example of an H bond or a hydrogen bond. Now, what I want you to notice is that when we're talking about, or I really like this image because of the fact that what we're seeing is the micro level connects to, or I'm sorry, the macro level connects to what's happening on the micro level. Here is our liquid. Here is our liquid. You can see it a little bit right here, but definitely if you were boiling water, you would be kind of capturing that water vapor, that hot steam on your face. Now, these are individual water molecules that are kind of floating away, or they're separating off. And so that's our connection between our macro and our micro level. In addition to all that, we always want to be able to communicate this and represent it symbolically. Here, what we have is a liquid converting to a gas. Now, we use the periodic table to kind of symbolize lots of different substances, individual atoms as well as compounds. We use different parts of this. We previously talked about our diatomic gases, and if you remember, H, bron, these are all our diatomic gases. Now, these are gases that at room temperature, they are going to be a gas, and these elements like to have two of these atoms come together to form one diatom or one compound. Now, let's go ahead and using the periodic table and a zoom pole, let's go ahead and answer this question. Watch. So what is the formula for helium gas? And you can toggle back and forth to the previous slide if you'd like. And the answer options are the same. The only difference is that the subscripts don't really translate into zoom poles. So we got 3 people that we're waiting on. I'm going to give you about 10 more seconds, and I will toggle back, and then we'll toggle forward. And now I'm going to go ahead and end the poll, and I'm going to share the results. Okay, so one person thought that it was HE with the subscript 2. And that's incorrect. Likewise, HE with the subscript of 3 is incorrect. It seems like everyone pretty much, or 4 out of the 5 people who answered said that it was HE helium. And you're absolutely right. Helium is not one of our diatomic gases. Yeah. So now, with that in mind, I'm going to stop the share of that. Close that. There you go. Chemical reactions are an important part of chemistry. Now, here what we have is carbon reacting with oxygen gas to form carbon dioxide. And that, rats. Just a second. I'm going to switch my share on that in just a second. So, if you've ever, like, here we go. So if you look at this, the caption for the video is reaction rate. Charcoal consists mostly of carbon and is typically obtained from wood by pyrolysis. So pyrolysis, if you think about pyrotechnics or pyromania, pyromania is an obsession with fire. Pyrotechnics is a technical understanding of fire. And so pyrotechnician would be someone who does fireworks, as an example, among many other things. Now, what we've got there is charcoal burns in a fairly slowly with a barely visible flame. In this combustion reaction, carbon dioxide is produced. We have C plus O2 to yield CO2. The rate of the reaction is limited by the concentration of O2 in the air, which, whenever I do this, the air concentration or the O2, the oxygen concentration is about 20%. So most of what I'm breathing in is carbon dioxide, nitrogen gas, carbon monoxide, but hopefully very, very little of that because that's poisonous and that poison can be fatal. When a stream of pure oxygen is blown on burning charcoal through a nozzle, which is what we are seeing in this. So here what we have is this O2 that is being blown directly onto this carbon. Now the reaction that's taking place is going to give us something that looks like fire. But this is an example of what's known as a combustion reaction, where we have carbon or a carbon-based substance and oxygen reacting with one another. Now, here is our overall reaction. C plus O2 yields CO2. Now, great question for y'all to answer and be able to answer is what are the states of each substance in this reaction? Well, our carbon is definitely a solid. It's pretty clear. We're blowing O2 onto this. So in order for that to take place, well, the O2 can't be a solid. Instead, it's being like flowed over it. So whenever I think of something flowing over something else, I think like water flowing over a rock, or oxygen gas, or air flowing over something. Now we note that, and we have to keep track of that. Our carbon is a solid. So we use a subscript S. So the proper rewrite of this would look something like this. Then our O2, that's a gas. So we're going to say plus O2 gas, and that's going to produce CO2, which is also carbon dioxide. is going to be a gas at room temperature. So we want to use those symbols to track solids, liquids, and gases, as well as something else called an aqueous substance, which we'll get into a little bit tomorrow. Now, if you remember, one of the things that we did earlier this semester was we looked at, all right, well, we combine these two solutions. Before our reaction, we had two separate containers, and with the glassware as well as the two solutions, they had a total mass of 173.64. Nothing was lost from our start to our end. Well, here was our end solution where we had our two different solutions that were combined together to have a mass of 173.64 grams. Now, whenever we have a reaction, sometimes we're going to produce a gas. Here, mercuric oxide is burned, so it's put under or put over a Bunsen burner, so an open flame, and we break that down into 92.61 grams of mercury and 7.39 grams of oxygen. The total resulting mass was equal to the total mass that we started with. Now, if you were doing it like this, well, you're not capturing that gas, but does that mean the gas is not produced? No, it just means that gas is released into the environment. Now, here what we have is an example of if you ever did a was a volcano in elementary school or middle school or anything like that, chances are you used vinegar and baking soda. Now, some people will also use sandstone, and you can produce a similar sort of reaction. What we've got here is vinegar, which has a mass. Into that mass, we're adding baking soda to that mass. And what's being produced in the process is carbon dioxide gas. So that gas mass is being released. And if you were to determine or weigh the contents of that beaker there, chances are it's just going to be equivalent to the mass of the liquid because the gas was released in that process. Now, what we always want to do is we want to consider this conservation of mass. What you put into something is what you get out of something. Now, here we've got a situation where, oh, if you're not capturing the gas, it might appear that you're not making any, but you're absolutely making some, and that gas does have mass. We want to balance a chemical reaction. Here we have water, which is electrolyzed. So you run water through an electric current or run an electric current through water, and you're going to produce hydrogen gas and oxygen gas. Now, this reaction right here, H2O yields H2 plus O2. What this shows us is we can kind of do some accounting. On this side of the reaction, on our reactant side, what do we have? We have hydrogen and oxygen. Now, the question is, how many hydrogen do we have? 2. How many oxygen do we have? 1. Okay, now let's go to our product side. We have hydrogen and we have oxygen. How many hydrogen do we have? 2. How many oxygen do we have? Also 2. So these aren't balanced. Now, one of the things that you have to understand, which, yeah, that's not balanced, is if I put a 2 down here, yeah, that balances it. But the problem is that whenever you, I guess, to put it bluntly, mess with subscripts, you are changing the compound. You're changing the substance that you're talking about. So I can't just put a 2 down here. Instead, the thing that you can do is you kind of play this little bit of a, it's almost like a game of volleyball or a game of tennis of sorts. You volley back and forth. You say, all right, well, what can I say that is balanced? My hydrogens are balanced. Great. Done. What you can mess with are coefficients. So I can put a 2 out in front of here. So now I need to kind of reevaluate. How many hydrogens do I have on my reactant side? Now I have, there's a 2, so I've got 2 water molecules. So that means I'm up to not 2, but instead 4. How many oxygens? Well, I don't have 1, I have 2. Okay, so now my oxygens are balanced, but that was at the cost of balancing my, or at the cost of having my hydrogens balanced. My hydrogens are no longer balanced. So what can I do? Is I can add a 2 coefficient in front of that. This is how I get to this. But also, what I've done is now I have 4 hydrogens, and that balances my hydrogens from my first intervention. So essentially, what you can do is play with coefficients in order to come up with the best balancing of the atoms, um, or best ratio of compounds in order to balance all of the atoms. Because to put it simply, however many hydrogens and oxygens your atoms of reactants must equal the atoms of your products. This statement right here is kind of the golden rule of balancing chemical reactions. It's not the number, but the identity of them has to be identical, or the number of the identified atoms has to be identical. If you have 14, yeah, 14 oxygens on the reactant side, 14 oxygens on the product side. If you have 36 magnesium, you got to have 36 magnesium on the other side. So we have to balance them by playing around with these coefficients. Now, here, what we were looking at earlier, the burning of solid carbon, that charcoal with O2. If we're making carbon monoxide, well, then what we have to do is we have to put a 2 in front of the C and put a 2 in front of the CO. Now, what we can see here is here's our start, and here's our end. This is a little bit tricky. You're basically volleying back and forth, back and forth, back and forth until you get it right. Now, these are these 2 reactions here, here, the third one, going back here. These are pretty simple and straightforward. Do they get a lot more complicated? They absolutely do. But the fundamental of this statement right here, number of atoms of reactants must equal the number of atoms of the products is going to be true. Now, in order to address this sort of thing, we also need to be able to look at a question like this. And let's go back. I'm giving my own advice, third direction. Let's answer this Zoom poll. How many oxygen atoms does MgOH2 contain? Does 3 MgOH2 have? I'm going to give you another 10 seconds. Okay, I'll give you a little bit more. But let's share the results. So we had 3 folks who said that it was 6, a couple who said that it was 2, and a couple that it was 3. Um, I think that this is a sort of question that can be inherently confusing because you might read it and say, okay, how many oxygen atoms does 3 MgOH2 have? Okay, well, I got to think about, well, is it, do I have 3 MgOH2s? Or is the asking if I have 1 MgOH2, how many do I have? In this question, another way that you could interpret this question or look at this question is you'd say, all right, well, how many oxygens do I have if I've got this? So the way that I always like to think about this is I've got, here's 1 MgOH2, here's another, and here's another. Now, what does X consist of? X looks like this. Now, is this the most accurate drawing of MgOH2? No, it's not. But MgOH2 is built from 1 Mg, 1 OH, and 1 OH. So if I've got this thing, and I've got 3 of them, I'm going to draw Mg. And just because I'm not a particularly good artist, my drawings might look a little bit different. Or my models of this compound might look a little different from one another. So here's 1, 2, 3. So I've got 3 of them. How many oxygen atoms do I have? There's 1, 2, 3, 4, 5, 6. So E6 is the correct answer. I can see how somebody might fall into the trap of saying, well, it's going to be 2 because you think, oh, well, that 3 doesn't matter. But it's there. So be thoughtful of like, you have 3 of these things. So process it that way. That's just to kind of like help you anticipate what's on the exam and quiz questions, sorts of things. Now, what is the formula? Sorry, I'm forgetting that I have my mouse, but it's not connected because I have a limited number of USB ports. What is the formula for iron 3 chloride? This is a little bit of a throwback. Iron 3 chloride. You got Fe3Cl, FeCl3, and 3FeCl. Give you another 15 seconds to think about this one. All right, that's going to wrap it up for this one. Sharing the results. The correct answer is FeCl3 because what this 3 shows us is it tells us that this iron is Fe3 plus. So it's just to kind of bring some things back. This is a cation. It's a positively charged ion. It has a 3 plus charge. Okay, then thinking about the periodic table, I'll jog back a little bit. So iron is right here. It's a transition metal, so it's kind of funky in terms of its charges. But if we've got Fe3 plus, then chlorine is right here. Chloride is the ion, the most common ion form of chlorine, and everything in this column likes to form a -1 ion. Here is a -2, and then here is a -3 for nitrogen. Now run back a little bit. So if we've got Fe, that's 3 plus, and Cl, that is minus, that means that we've got, I always like to draw it out, plus, plus, plus. Cl minus, okay, that's going to cancel. Cl minus, cancel. Cl minus, cancel. Okay, so those are my charge differences. That shows me an FeCl3 ratio, 3 chlorides. Now, this tool that I'm going to show you right here, this is a balancing chemical reactions little tool that you can play with. Okay, so here what we can do is we can visualize the reaction. Okay, so if we want to react carbon with O2 and make CO, that's 2 COs, 3 COs. Okay, so if I do that, then what does that say for my carbons? Well, I've got an equal number of carbons there. What about my oxygens? Well, I've got 2 oxygens as reactants because of 1 molecule of O2, but I've got 3 COs. So is my chemical reaction balanced at 3C as my coefficient plus my first reactant, 1O2 yields 3CO? No, it's not. If I do this, now all of a sudden, the number of oxygen atoms I have is too great. I've got 4 oxygen atoms, and I know that my products, I only need 3 oxygen atoms. So then I can either reduce my coefficients, which, you know, getting my carbons to equalize, that's not that big a deal. Here's 1 carbon, 1O2, and 3CO. Well, here my oxygens are balanced. My option is then to increase. So if I've got 6 CO and 3O2, I've got 6 oxygen on each side. Now I've got 6 carbon on each side. Let's see if I'm balanced here. Balanced, great. Is it simplified? No, it's not. So what does that mean? How can I simplify this? This is the second part of balancing a chemical reaction. The way that you can simplify it, oh man, I don't have an option but to show the answer, is all of these coefficients can be divided by 3. 6 can be divided by 3. 3 can be divided by 3. And again, 6 can be divided by 3. So I'm going to show my answer. So I come up with something as simple as that. And there we go. Next, now we're going to have CO2 breaking down into CO and O2. Well, if I have 1 CO2, that means I'm going to need at least 1 CO because then I'll have carbon and oxygen. Now, if I do this, well, I've got to actually, I know that O2 is one of my reactants because I'm told O2 is one of my reactants. So here I've got a ratio of 1 CO, 1O2. That gives me 3 oxygens. Well, that's out of whack. Okay, so how about this? Now I've got 2 COs and, or sorry, 2 carbons right here. 1 carbon. I need to up that. Oh, fine. 2 COs. Now I'm looking at, okay, oh, this is intriguing. What I needed to balance was my carbons. I've got 1 carbon, 2 carbon. I've got 1 carbon, 2 carbons. 1 oxygen, 2 oxygens, 3 oxygens, 4 oxygens. 1 oxygen, 2 oxygens, 3 oxygens, and 4 oxygens. It looks to me like I'm balanced. Let's go ahead and check this out. Yes, I did it. We're +2 there. So here you can now have carbon monoxide. I'm going to clear all my drawings. Carbon monoxide leads to C and CO2. So That's a game that you can kind of tinker around with. And that's definitely going to be the complexity of chemical reactions that I'm going to use for your exams. So the more comfortable you get with that, the better off you'll be for answering questions about balancing chemical reactions. Now, this is another poll here. Okay, so what this gives us is when the equation for the combustion of methane is CH4. This is a combustion reaction because we have CH4 and O2. So a combustion reaction by definition will be basically a hydrocarbon plus O2 yields two things. A combustion reaction will always yield these two things: carbon dioxide and H2O. So CO2 and H2O. Now, the question is, when the equation for the combustion reaction is balanced, what is the coefficient for O2? Okay, so here what we have is we've got to basically go through and say, all right, how many carbons do we have? How many hydrogens? How many oxygens on our reactant side and our product side? For our reactants and our product side, CHO, we got one carbon, four hydrogen, two hydrogen. Oxygens, we've got two hydrogen, and we've got three hydrogens. Okay, that presents a problem. Okay, now, one thing that I want to lead with is let's look at our different answer options. So we've got answer option A of 0. If there's a 0 in front of something, do you need that? No. That'd be like saying, hey, I need 2 grams of sugar and half a gram of flour and 0 grams of orange juice to make cookies. If somebody says they need 0 grams of orange juice to make cookies, do you need to get them any orange juice? No. So A is off the table. So for the person who answered A, I apologize, but that is not correct. Okay, so now we've got B through E, 1, 1.5, 2, and 3. Okay, so the question is really what's the coefficient in front of O2? So is it 1, 1.5, 2, or 3? Now, this C 1.5, we can cancel that out. And the reason we can cancel that out is whenever we're balancing a chemical reaction, we always want to use whole numbers. So 1.5 is out. So now we're left with B, B, or E. Okay. If it's 1, well, is it balanced? Effectively, what we're looking at right here, the coefficient is 1 in front of that O2. So what that means is that B is out of the picture. So now we're left with 2 or 3. And we know that B is out of the picture because of the fact that 1 in front of O2 would not balance it, because what we're looking at right here and here is out of sync. It's not balanced. So what I'm going to do is I'm going to erase some of these writings. Erase some of these markings, and then I'm just going to see what are the impacts of, let's say, putting a 2 in front of O2. What does that mean? That means that our oxygen is going to go up to 4. Okay. Now, the question doesn't say anything about you can't change any other coefficients. Instead, it's saying when you've got this balanced, what are the coefficients that you have? So effectively, what we could do is we could say, play around with some of these other coefficients. We could add a different coefficient. So, for example, what we could do is we could basically be responsive and say, all right, well, there's a 2 in front of O2. Let's put a 2 in front of H2O. And the reason that I did that is because whenever I do that, how many oxygens do I have? I've got two here, two more here. That brings my oxygen total up to four. Okay, so now my oxygens that were previously not balanced are balanced again. So I'm good there. Now, whenever I put that two in front of H2O, that means that now my hydrogens, well, it's not two anymore, but instead it's four. Did the two in front of O2 impact my carbons at all? It does not. So the correct answer for this is B, two. So in the poll, share the results. For those of you who answered two, you are correct. Good job. All right. So essentially, you always want to look for a whole number and your coefficient is not zero. If it's used in the equation, your coefficient is not going to be zero. The absence of a number being written there is just to mean that it's one. It's one CO2. So this right here, one CH4 plus two O2 yields one CO2 plus two H2O. That's a balanced chemical reaction. Plus zero Mg. Well, that'd be fine because zero Mg means that there's not magnesium there. But why would you write that? Well, you wouldn't write that because there's 118 elements in the periodic table. You would effectively be saying, oh, well, by process of elimination, I don't need that, I don't need that, I don't need that. That would be kind of silly. Okay. Now, practice balancing some chemical reactions. We've got NaN3 yields Na plus N2. I'm going to drink some water real quick. And I'm going to work with you on this one. So we've got these two species, NaN3. It's going to break down to Na plus N2. Are my NAs equal? They are. Great. I'm done. Except for the N. Okay, so how am I going to do that? Nitrogen. I've got to get nitrogen balanced. How can I balance these two? Well, let's start on the product side because that's a lower number. I've got two nitrogens on my product side. I've got three on my reactant side. So let's go ahead and let's up this from a one to, let's go ahead and, if I did a two, well, then it's still not balanced. But what I'm going to do is I'm instead going to say three. I'm going to put a three coefficient in front of N2. The reason for that is because I'm going to be able to come up with a common product. 3N2 means six nitrogens. If I put a 2 in front of NaN3, now I've got six. Why is it doing that? Six nitrogens. Okay. Does that throw off my sodiums? It does. Is that a problem? It's not. Okay, so that equation, that chemical reaction right there is balanced. Now, this next reaction, Fe2O3 plus C yields Fe plus CO2. You're given the hint to start with oxygen. Okay. Now, whenever I see this, I've got O3 and I've got O2. What did we just have? We just had N3, N2. How do we deal with that? We looked for a common product. So I'm going to do that. I'm going to say, all right, well, if I put a 3 in front of this and a 2 in front of this, what does that do for my oxygens? And I can go ahead and take stock of everything, F, E, O, and C. F, E, O, and C. My oxygens, well, there's 6 on each side. So effectively, that's done. Iron, okay, on my reactant side, I've got 4 iron. On my product side, I only have 1, but if I throw a 4 in front of that as a coefficient, well, that means I've got 4 irons. And I feel comfortable doing that because of the fact that, well, there's On the product side, it's just elemental iron. It's just the singular atom. I'm not throwing anything off. I'm not really causing a butterfly or a ripple effect or anything like that. Okay, so now my irons are balanced. What about carbons? Okay, so I've got on my reactant side, I have one carbon, and on my product side, I've got three carbons. Okay, it's a lot easier to put a three in front of this because, or it's sorry, it's very easy to put a three in front of that because now my carbons are balanced. Okay, so can I reduce this at all? Well, is there a common divisor? If two is divided by two, that's one. But if three is divided by two, that gives me does not give me a whole number. It gives me a 1.5. So that's not good. So none of these have a common divisor. So I'm not going to be able to reduce that at all. But I'm balanced. And I took stock of all of my atoms here and here respectively, and I equated them to one another. So in that same set balancing chemical reactions, this resource, you can do the same sort of thing. There's more. We're not going to do this, but this is just an exercise that I've previously done. Um, and so just an activity, an optional exercise for you to do, just for extra practice. Okay, we're moving on now to the discussion of the mole. What is a mole? A mole is a term to describe a number. Um, 1 dozen is 12 of something. If you have a dozen pens, you have 12 pens. A mole is the same thing, but it's tough to wrap your mind around because rather than 12 of something, which heck, if I had, if I look through my backpack because I'm an unfortunately kind of somewhat disorganized person, I could find a dozen pens in my backpack or my desk or something like that. But here we're talking about 6.02 times 10 to the 23rd. That positive exponent right there, that means that we are moving a decimal place 23 spots to the right. So this is the same as so if you say, "Oh, I have a mole of dollar bills," you've got that many dollar bills. If you think about this in terms of numbers that you're familiar with, okay, I'm going to go ahead and say, comma, 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 that would be comma, 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 comma. Okay, so let's put together a million. One, that's a million. A billion would be this. One, two, three commas. Um, let me do this. This would be 100,000. That is 100 million. That is 100 billion. 100 trillion. 100 quadrillion. 100 pentillion, I believe. And then this would be 602 hexillion, I believe is what that number is. So if you have a mole of dollar bills, you have, let's see, I think Jeff Bezos has like $600 billion or something like that. Um, you could buy Jeff Bezos's his boat like a million times. Yeah, I'm gonna go with that. So the point is, one mole is like 602 hexillion. Um, it's a huge quantity. And for that reason, it's tough to me personally, it's tough to like wrap my mind around it. I mean, heck, whenever I think about having $1 billion or something like that, just like that's a lot of money. If I had $1 billion, like billion single dollar bills, how much space would that occupy? That's just like it's such a large number that it's kind of mind numbing. So 602 hexillion particles is having a mole of particles. Now, this is also tricky because let's think about if you had 1 mole of pens versus 1 mole of, um, let's see, pieces of paper. Okay, they're going to take up different areas of space. They're not the same. 1 mole of pens is not the same as 1 mole of plastic cups. That's an important thing to wrap your mind around for our discussion of the mole. Now, there's cutesy things that we always do. For instance, in chemistry, people like to celebrate, maybe not celebrate, but have mole day. And that mole day is October 23rd. Why? Because 10/23. I remember the first time I heard of mole day, I was in high school and I was like, oh, we're not gonna do mole day because obviously it'd be June 2nd, but that's not the case. It's October 23rd. When I was in high school, I remember there was a friend of mine who was in a class where they got extra credit for making moles. And one guy, moles with different themes. So they had these little stuffy figures like this and could decorate their moles in different way. And there's one guy who was a big fan of the X-Men. And so he made Mole Nito. And another guy in his class was like, he, he was kind of rude. He said it was not very clever. I don't know. Mole Nito. At any rate, like I was saying, a mole of pen versus a mole of pieces of paper versus a mole of you know socks. I'm just looking around at things that I have in my area. They're going to be different. For instance, these what are shown here are all 1 mole samples. Now, do all of these 1 mole samples look the same? No, they don't. One, helium is not a purple balloon. Instead, what's being said here is that helium is captured in this balloon, this helium gas. 1 mole of helium gas is in that balloon. What we also got is 1 mole of sulfur, not to be mistaken with like a lemon bar or a lemon flavored pound cake. We've got 1 mole of mercury, 1 mole of iron, and 1 mole of copper wire. Now, these things look drastically different because they are. The makeup of copper, iron, sulfur, mercury, helium, they are all different from one another. They have different masses because the individual atoms, a copper atom, is different from an iron atom. And I'm going to jog back a second. If we look at the periodic table and we look at a helium atom versus a sulfur atom versus an iron atom, one atom of iron has 26 protons. One atom of sulfur has 16 protons. These atoms are different from one another, and that's going to display itself in what these samples look like. Now, a dozen It's going to be the same thing if you're talking about a dozen eggs versus a dozen nails or a dozen yellow roses. They're going to have different properties. They're going to have different masses. They're going to occupy different spaces. So think about that whenever you're trying to, work to wrap your mind around the concept of a mole. Now, what does a mole weigh? Molar mass is the mass of 1 mole of a substance. Okay. 1 mole of copper has the mass of 63.5 grams. 1 mole of sulfur. This is sulfur, not, oh, no, that kind of looks like ricotta cheese, or it looks like some feta cheese, but kind of dried feta cheese, or maybe it's not. No, yeah, it's ricotta. I think it's ricotta cheese that I'm thinking of. This is sulfur, not to be mistaken with any of those other cheeses or non-cheese substances that look similar. That has a mass of 32.1 grams. 1 mass of copper, again, we're talking, or carbon. Again, we're talking about carbon being that charcoal. That's approximately 12 grams. Now, if we look at the periodic table, we have the average atomic mass of one atom of copper is 12 point, why is it doing that? I don't know. 12.011 AMU. 63.5 AMU. The reason for that is if you have exactly 1 mole of copper, it it is going to be 6.02 times 10 to the 23rd atoms of copper with this specific mass. And we can say each one of those atoms has that AMU, or atomic mass unit. And because of that, we can say 1 mole of carbon is 12.011 grams per mole. Now, if we look at these options, helium, copper, iron, sulfur, mercury, which one of these is going to have the greatest mass? Okay, well, we know that helium with an atomic number of 2, copper 63.55. I'm going to toggle back and forth between the periodic table, but your screen won't show this. Iron, oh darn it, that periodic table that I had done, dtable.com is where I'm going. dtable.com. Iron is 55.85. Sulfur is 32.06. And where mercury 200.59. So if you have 1 mole of each of these things, mercury has the greatest mass. Okay. So if we make a compound, if you have 1 mole of CO2, you have 1 mole of CO2, I always try to think about this sort of thing, saying, well, if I have 1 mole of CO2, let's instead make that a simpler number. Let's say that you have 10 CO2 molecules. Now how many carbons, oxygen do you have? You have 10 carbons and you have 20 oxygens. So now if you have, let's erase all that, erase by scribbling. If you have 1 mole CO2, you have 6.02 times 10 to the 23rd carbons, which is the same as saying you have 1 mole of carbon atoms, C atoms. Then you have 2 moles of oxygen atoms, which is the same as saying that you have 12.02 times 10 to the 23rd oxygen atoms. Now the mass of each of these, well, 12.01 plus That's the mass of that. 2 times 15.99. So 15.99, let's round that up to 16. So we've got 2 times 16. That is 32 plus 12 equals 44. That's how we get the molar mass of a compound. The molar mass of an atom or the molar mass of an element is on the periodic table. It's this right here. So if you had 1 mole of nitrogen, that would have a mass of 14.07. But with that said, what do we know about nitrogen? Nitrogen loves to exist as a diatomic element, so N2. So if you have 1 mole of N2, you actually have 2 times 14.007, which is 28 grams of N2. Now, our last Zoom question of the day, or a Zoom poll question of the day. Back. Launch. Launch. What is the molar mass of 1 mole of N2? I clicked launch several times and now it's going. Is it 14, 16, 30, 44, or 46 grams? We got 2 votes for 46. I'll give you another 10 seconds on this question. All right. We're going to stop the poll, share the results. Each oxygen, there's 2 of them. Those add up to about 32 plus 14. Good job, y'all. Stop sharing. That's me narrating the work. Okay, great job. Converting mass to moles. Well, 18 grams of H2O, 8 grams of Br2. We got to use the periodic table for this. So if we have 1.8 grams of H2O, we're working in the opposite direction. 1 gram of H2O. What is the mass of 1 mole of H2O? We can do something known as dimensional analysis. And this is merely a conversion. So what I'm going to do is I'm going to write what I started with. And then I'm going to draw this nice little picket fence here. And on this side right here, I'm going to write with what I want to end with. And I want to end with moles of H2O. And I'm going to come up with a ratio that is 1 mole H2O. What dimensional analysis allows me to do is multiply across the top and then divide by the product of what's on the bottom. Now, I remember that oxygen has a mass of 0, which I see right here. Hydrogen has a mass of 1. So that means that 1 mole of H2O is 18 grams of H2O. So I'm writing my kind of equivalency statement right here. So 1.8 divided by 18 would be 0.1 mole of H2O. This is dimensional analysis, and we're going to do the exact same thing over here. 8.0 grams of Br2. Okay, now what is 1 mole of Br2? And then what's the mass of bromine? I got to pull this from the periodic table, and that is 80. Br is 80. So what does that mean for 1 mole of Br2? It's 160 grams of Br2. This is a question that's intentionally kind of tempting and deceiving for you to say, oh, well, it's got to be 8. But remember, bromine is a diatomic gas. So you're going to say 8 divided by 160. And you're going to come up with an answer that is 0.05 moles of Br2. So the identity of the gas is, or the identity of the substance is important to know. Now, converting from moles to mass, we have 0.1 mole of CuSO4. That's a compound known as copper sulfate. Okay, so now what we're going to do is we're starting with 0.1 mole of CuSO4. What I want to end with is the mass of Cu104, grams of CuSO4. Okay, what is the mass of copper? Copper is 63.55. So I'm going to write this out. I'm going to detail everything. Cu is 63.55. S is 32.06. Oxygen, there's 4 of them, and each one is 16. So I'm going to say 16 times 4 equals 64. So this essentially gives me 63 and a half plus 32 plus 64. So that means 32 plus 64, this adds up to 96 plus 63.55. And that's going to give me 159.55. I believe that's correct. Yeah. Okay, so that means what I can write here is 159.55 grams of CuSO4 is the mass of 1 mole of CuSO4. So 0.1 times 159.55. And that gives me 15.955 grams of CuSO4. Okay, so we can look back at the previous slide and we can see that the mass of 1 mole of H2O, 1 mole of Br2, 1 mole of CuSO4, these masses are all different from one another. So if you said you had 1 mole of this substance or 1 mole of this substance, that's the same as saying, oh, I have 1 mole of Oreos. And someone else saying, oh, well, great, I have 1 mole of bacon, egg, and cheese breakfast tacos. Are the masses of those two things going to be the same? No, they're not, because the individual breakfast taco and Oreos have different masses. Now we'll do this other calculation right here. We're starting with what we're given, 0.1 mole of K2Cr2O7. Now, what I want to end with is the mass of K2Cr2O7. I've got to add up. What's the mass of K? I'm going to say, what's the mass of Cr and what's the mass of O? Well, I know that oxygen, just because I've used it so much, I know that oxygen has a mass of 16. So 16 times 7. 6 times 7 is 42 plus 70 is 112. Okay. Cr. I got 2 CRs. And Cr is 52. It's 51.996. I'm going to call it 52. Times 2 equals 104. Potassium is K. It's 39.1. Times 2 equals 39 times 2 would be, see, that's 78.2. So now I'm going to take all those 78.2 plus 104 plus 112. And I'm going to get 294.2 grams of K2 Cr2O7. That is 1 mole of K2Cr2O7. So if I'm looking for the mass of 0.1 moles, well, 294.2 times 0.1, that's the same as saying 10% of this. So I'm just multiplying, I'm moving this decimal place one spot. So 1 mole of K2, or sorry, 0.1 moles of K2Cr2O7 has a mass of 29.42 grams of K2Cr2O7. All right. Now, here, how many atoms of helium are in a balloon filled with 1 mole of helium? I love this sort of question. And this is going to be a sort of question that is going to be an important one for you to be able to answer because to me, this is kind of a logic based question. It's taking a pretty complex topic and asking a very kind of blunt question of like, do you understand this on a basic level? Yes or no? Okay. So let's look at this. How many atoms of helium are in a balloon filled with 1 mole of helium? What is 1 mole of anything? 1 mole of pens is 6.02 times 10 to the 23rd pens. We can quantify it. We can say it's not 2 pens, it's not 1 pen, it's 6.02 times 10 to the 23rd. It's 602 hexillion pens. So if you have 1 mole of helium, what is kind of left off here, what is the singular unit of helium? Well, it's an atom. 1 atom, if you have 1 mole of helium atoms, you have 1 atom. Oh yeah, you got more than that. So it's not 1. That's not my best answer. Do you have 2 atoms? Yeah, you also have more than that. What about 4 atoms? Oh, you got more than that. What about 22.4 atoms? Ooh, that's kind of a tricky question. That's kind of an arbitrary one, but you've got more than that. In addition to that, you can't talk about like zero point 0.4 atoms. Your correct answer is E, 6.02 times 10 to the 23rd atoms. In summary, you can take number of moles and go to molar mass. And then you could also take number of moles and figure out how many, using Avogadro's number, how many atoms or molecules you have. Being able to do this, being able to go from one to the other. Like if I said I have 128 or 1.28 times 10 to the 25th atoms of argon gas. A question that I could ask is, do I have 1 mole of argon gases? How many moles of argon gas? Well, I know that 6.02 times 10 to the 23rd. Sorry, times 10 to the 20. I don't know why it's doing that to me. If I have 6.02 times 10 to the 23rd atoms of argon gas, this is equal to 1 mole of argon gas. Well, if I have this many, essentially the question is 1.28 times 10 to the 25th greater than 6.02 times 10 to the 23rd? Yes, it is. And if you're looking at this and you're like, oh man, I don't know, do I need to divide this? This sort of number, you can just look at the exponent. 25 is larger than 23. Really, this number and this number, they don't matter. If you were to look at 1.28 times 10 to the 23rd versus 6.02 times 10 to the 23rd, well then, which one of these numbers is larger? Well, the exponents The exponents are the same, so we don't care about those. So we can scribble that out. And if I'm asking you which is the larger number, what's bigger, 6 or 1? 6. So this is your larger number. So being able to do calculations where you go from number of atoms or molecules to moles and moles to mass, that's going to be instrumental in working through this sort of chapter. Now, the questions that I'm going to ask on quizzes and exams, quite a few of them are going to be like this. But then there's also going to be questions like this, doing these conversions. Make sure that you know how to do this sort of conversion as well as this sort of conversion. These are going to be extremely helpful and powerful. Okay, we have a quiz that goes live at 12 today. That is due tomorrow at 2 p.m. If you have any questions, please don't hesitate to contact me, and I can set up either an office hour where we can meet and maybe work through some practice problems. Um, but I would definitely use the periodic table, or come up with your own sorts of questions like this. What's the molar mass of O2? What's the molar mass of N2? Just make up combinations of molecules or make up combinations of atoms and try to calculate the molar mass. Um, and that will be very helpful. Um, at any rate, I'm going to go ahead and stop my share and I'm going to stop the recording. Um, if you have any questions, please feel free to contact me and I'd love to help out as much as I can. All right. Have a good one.